2005, and we looked at how much area burn might we see in the future. And there's a whole bunch of these papers out there now, and 3 times CO2, carbon dioxide, scenarios, end of century basically, or equivalent, 3 times CO2. So we're suggesting a doubling of area burn for Canada by the end of the century. This is conservative to many of the papers that come out there. Some are suggesting increases of 4 times, 6 times, 8 times. And yes, at some point, if you get that much fire, your forest will disappear, okay, because they just cannot handle that much fire. But what replaces the forest? And we just heard, it depends where you are. It could be grasslands, it could be all sorts of things. But the key thing here is you'd still have fuel, you still have ignitions, you still have hot, dry, windy weather. You'll still have fire, regardless of what's there. So, and we've heard that temperature is very important. And the work I've done and other colleagues has found in Canada, the United States, and Russia, and Alaska, that temperature is really important for fire. And I get asked all the time, why is temperature so important? Well, longer fire seasons, okay? And in Alberta, our official fire season start is now March 1st. It used to be April 1st, so it's a month earlier, and we're actually seeing our fire season start earlier. Not this year, but the previous 2 years, we had actionable fires in February. And arguably, I would say Alberta is close to a 12-month fire season already, as are many parts of the United States. Longer fire seasons. Second, the warmer we get, the more lightning we have. The more lightning we have, the more fires we have, everything else being equal. Work done in the United States suggests for every degree of warming, there's an increase of about 12% in lightning activity. Work has not been done for Canada, to my knowledge, but I would expect similar numbers for Canada. The third reason is probably the most important, is drier fuels. The atmosphere, as the temperature warms, it can hold more moisture. And that change in the moisture capacity is exponential. What it means is, as it warms, the ability of the atmosphere to suck moisture out of fuel increases exponentially. Now, unless there's an increase in precipitation which can compensate for this, our fuels will be drier. And how much precipitation would you need? Well, work we did said for every degree of warming, you need about a 15% increase in precipitation. So let's say this region warms 2-3 degrees. That means you need a 30 to 45% increase in precipitation during the fire season. And what we've seen, that's not going to happen, and that's what other model scenarios suggest. That's not going to happen. Bottom line, if we see this warming, our fuels will be drier. Drier fuels means easier for fires to start and spread. So I'm going to present some work on head fire intensity, HFI. And this is an important threshold for fire management because as you get to 2,000 kilowatts per meter of fire line, and that's a flame about 2 meters or so, it becomes unsafe to have crews on the fire line. It's just too dangerous, okay? Some people use 4,000, some using 2,000, but in that ballpark. And then at 10,000 kilowatts per meter, fire intensity, aerial attack becomes ineffective. So if you get a fire above 10,000, your options are limited to indirect attack, either backburning or evacuations and waiting for the weather to change or to run out of fuel or hit a fuel break it can't jump across. So you're quite limited. 10,000, and most crown fires in arboreal, 20,000, 30,000 kilowatts per meter. So if you have a crown fire, it's very difficult to control. The picture here is the fire coming into Slave Lake in 2011. It's May 15th. The winds are close to 100 clicks. Eventually, aircraft were grounded. Spot fires were occurring in town when the head of the fire was still 2 kilometers away from town. So very difficult to deal with. This is the fuels we use. We use the Canadian Forest Fire Danger Rating System, specifically the FWI, the Fire Weather Index System, and the FBP, the Fire Behavior Prediction System. So my talk is 10 minutes longer because I'm explaining every acronym. So when we looked at time periods throughout this century, and we used fuel data from the Canadian Forest Service, CFS, and we considered fuels to be static. I know that's probably not going to happen, but that's a starting point, and as we move along, we'll have more dynamic fuels. But a mature tree isn't going to disappear unless there's a catalyst of change, like Greg was talking about, like fire, for example. So now these are built-in animations, maybe, and maybe not. Okay. So, hey, the built-ins work. Okay. So you can see 2000. What you're seeing is the representative concentration pathways, RCPs, for we try and get our act together versus kind of a more business as usual, 8.5, kind of early century, late century. And what this suggests is the number of days above 2,000 kilowatts is increasing up to 60 days in some parts of BC. So now we look at 10,000. This is where aerial attack becomes less effective or arguably ineffective. And once again, you cycle through the concentration pathways and the time periods, and you can see that by end of the century, the most pessimistic one, we're getting 40 days or more where you could have these high intensity crown fires. These are additional 40 days to what the standard, the average is. So it means a much longer period where we could have unmanageable fires if you do not put out when the fire is small. So we also looked at surface and crown fuel consumption using these models. We used 3 GCMs and the 3 standard concentration pathways. And what it suggests is that there's going to be a lot more greenhouse gas emissions as you move to the warmer, drier Hadley model versus the cooler, wetter Canadian model. And this is different from earlier work that suggested that most of the increases in greenhouse gases from fire would come from increases in area burned. Now it's saying it's coming from increases in area burned and because more fuel is being consumed because the fuel's drier. So more greenhouse gas emissions. I don't have time to talk about the carbon dynamics of fire, but we've heard that temperature, the warmer it is, the more fires we see. So the more fires we see, the more greenhouse gases we have. The more greenhouse gases we have, the warmer it gets, and it's called a positive feedback. And globally, greenhouse gas emissions from fires are very significant. So we've heard a bit about this, and I'd like to carry on a bit about wildcard. Work done by Michael Mann last year suggested that we've known about the jet stream becoming more stagnant for a number of years now. Last year, Michael Mann did a paper saying that the changing jet stream is changing the extreme weather we're seeing, whether it's flooding or drought. Fire people have known since the 50s that ridges are important to fire, and what we call blocking ridges, and that's kind of sometimes called omega block because it's like the Greek letter omega, and that means a ridge just parks over an area like British Columbia last year and California last year as well, and it just sits there 7-10 days or longer. Last year a lot longer, and it's kind of the opposite of your grade 3 water cycle. So what happens in a high pressure system is air sinks and warms and dries, okay? Generally sunny conditions, so it's getting the fuels nice and dry, ready to burn. And that's why a wet spring's not, or a wet winter and a wet spring aren't really critical to fire in most vegetation types. For peatlands it's different. But you give me 7 to 10 dry days, your fuels are now available to burn. So that's what happens with a ridge. Now, in the low pressure systems or the troughs, grade 3 water cycle, air rises, cools, condenses, cloud forms, and then precipitation. So with our jet stream getting weaker as described earlier, the temperature difference is getting weaker because of the higher latitudes are warming much more rapidly than equatorial areas. It's becoming lazy. It's like a lazy river, and we get this stagnation where the ridges are parked for longer periods of time and are more intense. Some people are worried that typically in summer we see a ridge along the west coast of North America. That's the normal position, but it seems to be staying longer and stronger than before. And there's work because of the Arctic ice is melting that's anchoring that ridge, and they're worried about becoming a permanent feature where it just sits there basically most of the year, which means desert-like conditions under that ridge area, which runs from California up through Oregon, Washington, British Columbia. So how can we manage fire, wildland fire? So, three ingredients: fuel, ignitions, and weather. We can't do anything meaningfully about day-to-day weather right now. Globally, we can do something about climate change and getting our act together and reducing fossil fuels emissions and doing other things. Ignitions, we can't do anything about lightning. We can and do things about human-caused fires. Every human-caused fire is preventable. A number of the fires in California were caused by power lines, okay? You can bury power lines, and they tell me that's expensive. Well, the bill hasn't come in for California yet, but it's being measured in the tens of billions of dollars. Probably 40 to 50 are the numbers I hear kicking around. Those are guesses, but well exceeding 10 or 20. 10 and 20 just went flying by. So, or if you keep them above ground, you have to maintain them properly so they can withstand the strong winds, the increasingly strong winds. That's one thing about climate change is the wind speed average for most of these models is about the same, but we're seeing the distribution change so that we get more extreme wind events. And we just had one here recently. We had one in Alberta last week, and it's kind of an unusual time of year for the extreme winds. But extreme winds and fire go hand in hand for individual fires. Very critical aspect. So the other aspect is fuel. And there's things like fire smart programs where we talk about managing fuels around communities. So there's other things we can do. The Canadian Forest Fire Danger Rating System is a great system. It's parts of it are 40 to 50 years old. The amount of information and data we have has changed significantly. The demands on fire management has changed significantly in those periods. It's time to update this. An improved early warning system using machine learning. We use self-organizing maps that uses the upper atmosphere, those blocking ridges, and the surface maps to help predict episodes of extreme fire weather behavior, extreme fire weather, pardon me. And we can use machine learning for fire occurrence prediction, so we have a better idea of when and where those fires will occur and how severe they might be, and so that you can be better prepared by moving resources to a proper place. And machine learning, artificial intelligence, it's not here to replace existing systems, it's here to enhance existing systems. Our focus should be on community zones, and when and where possible, allow fire to burn in the back areas, the back 40. And you can explore fuel management in concert with harvesting, grazing, and carbon management. And this figure here, actually it's a remote sensing image, and it may be a little hard to see, but it's the nighttime light images. And if I can move my mouse here, you can't see my mouse. Okay, Nelson's in the center there, and the 2017 fires are outlined in red, the polygons. So you can kind of see where the wildland urban interface and fires interact. And of course, sprinklers are an option to use around communities and are very effective. So I'm going to wrap up in a few summary slides here. Fire and weather are strongly linked. Changes in forest fires may be the greatest early impact of climate change on forests. People may argue Mount Pine Beetle, and they would have an argument to discuss. Fire activity will increase, but be variable in time and space. Oh, those two pictures, the top one I took in Fort McMurray, May 2016, up above waterways, if you know the community, and there's a little fire smoldering there, and this is a few weeks after the fire went through, and you look down the valley and you can see 20, 30 of these little fires burning. And if you look really closely, you'll see some aspen coming up in the foreground. And this is just a few weeks, and aspen's already coming up. My student took a picture in the bottom, and that was the fall of 2016, and it's like that carpet of aspen coming back up. So, longer fire seasons. And really, what is of concern is, with these longer fire seasons, we're seeing high-intensity fires outside the historical, traditional area. And so sometimes we may be getting caught saying, oh, we don't get high-intensity fires in Fort McMurray on May 1st, okay? It just doesn't happen. It's never happened. But yet our fire danger system was saying, look out, you know, it's 100th percentile. Look out. But no, we don't get fires, and we get them down in Lac La Biche. We get a lot of fires in May, but it's farther south. Usually the Fort Mac fires are more of a summer boreal fire situation. And BC, we had fires last year, July 7th. We normally don't get high-intensity fires early in July. It's later in July, and August is the busiest month for BC fire activity. So this is really, really early. So having high-intensity fires outside the normal range is really challenging. We'll see more fire occurrence, work done by Mike Watton, more crown fires, higher intensity, more fuel consumption, more area burned, more fire activity in the future. Our management approaches have to adapt to this new reality. So I'll leave you with a question. So what will the 2018 fire season hold for Canada and BC? It's already started, and we're off to a quick start, but what's the rest going to be like? We'll see. Here's the slide I talked about, and 2017, head and shoulders above 1958 was the previous high for BC, about 880,000 hectares, and 61 was, you know, so it's been a long span before something like 1.2 million hectares. And here's the sponsors that sponsor our work. Thank you very much.